In the last chapter, we learned that information is represented by numbers and at the lowest hardware level is represented or carried by the physical parameters of carriers. In quantum technology, qubits and quantum gates are the smallest components of a quantum computer. Qubits are the information carriers, and gates change the parameters of qubits, thereby performing information processing, including computation. A fundamental advantage of quantum technology is that an ideal qubit is free from noise-induced errors. How can we make an error-free qubit? One obvious solution is to make its parameters discrete whenever possible. From the previous chapter, we know that energy or mass and their related amplitude parameter are naturally discrete without any special effort from hardware engineers. How do we make the other parameters discrete? Let us look at how a guitar string produces a clear, noise-free note. Its vibration is constrained at two ends, one at the bridge and the other at a fret. As a result, its vibration frequencies become discrete. By the same principle, when an electron wave is trapped or bound by a positively charged nucleus in an atom, its three spatial parameters become discrete. This is why atomic orbitals are discrete. Quantum computer startups such as Quera and IonQ take advantage of this principle to build neutral atom and ion trap qubits. These are among the most promising types of qubits. Integrated photonic qubits are another promising type. Optical fibers, or waveguides in general, are like water pipes and allow light to propagate within them without leaking out. Two-dimensional confinement in a waveguide turns two spatial parameters of a photon into discrete modes. Another parameter is fixed by the light source. A photon traveling in a fiber or even in free space makes a good qubit for quantum communication. It uses its polarization and phase parameters to represent information. Other types of qubits may use different parameters, but their encoding or mathematical abstraction is the same. Therefore, throughout these lectures, when the type of qubit is not specified, the term qubit refers to a photonic qubit. It is unlikely that we will build a quantum computer entirely from quantum devices. Instead, qubits and quantum gates will be contained in a quantum coprocessor within a conventional computer. We may call this coprocessor a quantum processing unit, or QPU, following the naming convention of CPU and GPU. When faced with a demanding computation task, a software program directs the QPU to assemble a circuit of qubits and quantum gates to accomplish it. The 3 lines of Python code shown here call the IBM QPU to begin building such a circuit. In 1985, David Deutsch proved that any computing task can be accomplished by a series of unitary matrix multiplications. Earlier in 1980, Richard Feynman had proposed that such mathematical computations could be carried out by a quantum process that emulates the same matrix multiplication. Their work suggests that quantum computers can accomplish any computation task and are therefore universal, provided that we can find a corresponding quantum process. But can we always find such a process? The answer is that we do not need to find one. We can simply build one. In 1995, Solovey suggested, and in 1997, Kitaev proved that any unitary matrix can be implemented by a circuit constructed from a small set of 5 standard quantum gates as building blocks. All we need, therefore, is a QPU that contains a pool of qubits and these standard gates. Here is a sample Python program that calls an IBM QPU. It first imports the IBM Qiskit software package and connects to the back-end QPU in lines 1 and 2. Line 7 initializes a circuit with 1 qubit and 1 classical bit. Line 9 applies an X quantum gate to change the value of the qubit. Line 11 applies a measurement gate to read the value of the qubit. We will explain what this program is for when we study the circuit it builds shortly. We know that any computation task can be broken up into a series of unitary matrix multiplication subtasks. Each subtask multiplies a vector of complex numbers by a matrix, U, also composed of complex numbers. The vector is the encoding of a set of n qubits, which our program first calls on the back-end QPU to allocate. The number n is determined by the needs of the subtask. This vector, or encoding, is the mathematical abstraction or representation of the qubit's wave parameters and serves as the code through which software interfaces with the hardware. Upon allocation, the qubit's wave parameters default to 0, and therefore the encoding of the qubits defaults to the 0 vector. We then build a sub-circuit of gates to set the parameters according to a vector that encodes the input data for the subtask. The subtask at hand is to multiply the input vector by the unitary matrix U. The computing sub-circuit we build changes or transforms the qubit parameters in a way that is equivalent at the encoding level to multiplying the input vector by the desired matrix, U. The last part of the circuit is usually the readout of the qubits. One consequence of the qubit readout bottleneck, which we will discuss in the next chapter, is that a qubit cannot be used again once it is measured for readout. In this diagram, we see that the qubits, which are waves, propagate to the right into the input and compute sub-circuits before being measured. The information processing or computing scheme is very different from how a conventional CPU works. A conventional CPU does not operate on a whole vector at once. It follows a clocked sequential process known as the fetch-decode-execute cycle. In each clock cycle, the CPU fetches one instruction from memory, decodes it, and executes it using arithmetic logic units built from billions of transistors. Even when we say a CPU performs parallel computing, it typically means that multiple cores or vector units are executing many small arithmetic steps in parallel. But each multiplication, addition, or memory access is still broken down into discrete transistor-level switching events, controlled step by step by the clock. If a classical computer needs to multiply a large complex vector by a matrix, it must compute each product and sum element by element. That means many multiply and add operations, each carried out in sequence across clock cycles. Even if some are pipelined or vectorized, the larger the matrix, the more individual arithmetic steps are required. Running the qubits through a quantum circuit once, however, is considered one operation. The matrix multiplication accomplished by this single circuit operation would usually take many steps on a conventional computer. In other words, a computation task that requires many sequential arithmetic steps on a conventional CPU can be accomplished concurrently in one quantum operation at the level of the encoded vector. This concurrent computing capability is what gives quantum computing its power. The Python program implements this simple quantum communication protocol. This is neither a practical nor a useful protocol. The sole purpose of this example is to show how an application can be enabled by the special properties of qubits and how to draw a quantum circuit diagram. Engineers often describe communication scenarios using a standard narrative. Alice wants to transmit a sequence of bits to Bob, but is concerned about Eve, who may attempt to eavesdrop. In a conventional communication system such as Wi-Fi, Alice's device sends bits sequentially, 1 bit per clock cycle. Each bit is carried by a radio wave whose polarization angle, 0 or 1/2 of pi, to represent 0 or 1 respectively. Eve may intercept a portion of the wave and recover the bit, while Bob receives the remaining portion without being aware of Eve's eavesdropping. However, if the wave sent by Alice has only a single unit of energy, in other words, if it is a qubit, Eve must either capture the entire quantum of energy or capture nothing at all. Partial interception is not possible. If Eve succeeds in capturing the qubit, Bob observes the absence of a qubit in that clock cycle and can therefore detect that eavesdropping has occurred. Again, the goal here is not to demonstrate the usefulness of this crude scheme or protocol. Rather, the goal is to illustrate how quantum properties can be exploited. We also want to show how such a quantum communication protocol or algorithm can be described using a quantum circuit diagram as shown here. In this diagram, a single line represents a qubit wave, while a double line represents a transmission line carrying conventional digital signals. Each rectangular box represents a gate. A gate modifies the parameters of the qubit and therefore the information it carries. In each clock cycle, the qubit that Alice initializes has the default code of 0. The qubit then propagates to an X gate, which can change the qubit's polarization parameter to 90 degrees and flip its code to 1. In this scenario, however, the X gate is controlled by the input digital signal from Alice. The qubit is flipped to 1 only if the corresponding data bit in that clock cycle is 1. As a result, the qubit's code in each clock cycle is set by the input data bit. In this simple protocol, there is no information processing or computing circuit. On the output side, Bob uses a measurement gate to read out the qubit's code. The red dashed line in the middle of the circuit represents a point of notation and, in this example, indicates the parameter theta of the qubit waves transmitted during the 4 clock cycles. The advantage of using quantum circuit diagrams is that both the hardware codes transmitted by Alice and the carrier parameters of the qubits can be shown in the same diagram. Here we have mentioned some of the details in a hand-waving manner. We will address them in the next chapter. Let us pause here for 2 exercise questions.